So this is Toby here. I'm gonna give you a lecture today about time domain responses of some low pass and high pass filters, small signal, large signal, what you can do with these follower integrator and follower differentiator circuits. And this first time we'll be talking about the time domain. So far it was all static circuits, like basically DC steady state response. And now you're gonna talk about temporal response processing. Okay, you see the whiteboard okay? Okay, so this is all about time domain. And basically what we're going to do here is we're going to study two simple circuits. The basic first order low pass filter, which is an RC low pass, where V1 is the input and V2 is the output. And I think probably everybody understands that the V2 here represents a smooth version of V1. The resistor just lets the charge dribble onto or off this capacitor at a rate that's set by the RC time constant. And so V2 is the same as V1 if V1 doesn't change, right? It's clear that if V1 doesn't change anymore, then V2 will just equal it after a while because there would be no more charge flowing on the capacitor. But if V1 changes quickly, then V2 won't follow it. So this is a low pass. And in fact, the frequency domain response of this thing, you can almost guess what it looks like if I have frequency on this axis and a log scale, and I put the log of the gain, the log of the magnitude of V2 over V1, which is also called H. I don't know why they call it H, but anyway, the magnitude of V2 over V1 is usually called H. It's a function called H of F or omega. What is that going to look like? Well, it'll have a gain of 1 here for low frequency, and then at a certain frequency it'll start to roll off, and it's a first order low pass. So the slope here will be -1. And now to make a CMOS circuit out of this, because you can't usually build these resistors, or if you do build them, they're really large area if you want a large resistance. And you need a large resistance because you can't make a big capacitance. So if you want a long time constant, you need a combination of big capacitance or big resistance or some big product of them. And also, in case you want to control the resistance value, you can't change that after you build a resistor. So typically what people do is they replace this resistor with a transconductance amplifier, right? So it'll look like this. Now, why does this transconductance amplifier act like this resistor up above? Well, the resistor makes an output current that's proportional to the difference of voltage across it, right? If you wire up the transconductance amplifier with a transconductance G like this, isn't that exactly the same thing that's doing? The output current here for small signal, when the voltage isn't too big, the output current proportional to the difference between the two inputs, which is the difference between the input V1 and the output V2. So in terms of the output of this transconductance amplifier, it acts just like a resistor. Of course, it doesn't consume current at its input like a resistor. That makes it good, actually, in some ways, because it doesn't load down the input with some conductance. It's just you're driving a gate. But in terms of the circuit property, as long as the signals are small enough that you're in the linear range of this transconductance amplifier, you remember it has this transfer function that looks like this. This is delta V and this is I out. As long as you're in this linear range in the middle, it kind of acts like a resistor. And so that's the CMOS equivalent of this RC low pass filter. Is that clear? Okay. So the dual of that circuit. Yeah.
So could you repeat this part again? Just until we are, you said when we are in the middle of differential voltage over E, it has something like a resistor. Is that what you said?
Yeah, when the voltage, yeah, thank you for asking that question. That's a good question. So when this delta V is small here, the slope of this curve is G, is the conductance of this transconductance amplifier, right? And so, but as long as the voltage difference is small, so in other words, if V1 minus V2 is a small voltage, less than about 100 plus or minus 100 millivolts, then the output current will be linear with the voltage difference, just like it is for the resistor up here, right?
Okay.
But if I suddenly make, if V2 is sitting at 1 volt and I suddenly make V1 2 volts, what will happen? All of a sudden the delta V will be way over here. Now the current is not proportional to the difference of the voltage anymore. It's just a constant current. In this whole range, the current will just be constant. That's not what you want, right? Then it won't be like a resistor anymore.
Yeah.
Is that clear?
Okay. Okay.
Well, it's what's called slew rate limited.
Oh, okay.
In other words, it'll only change the output. Stupid pen is always pressing the button by mistake. It'll only change the voltage linearly with time because it'll be a constant current charging a capacitor, which is not what the RC filter does. This thing is linear no matter what the voltage. Right?
Okay.
A real resistor like this one up here would act like that, right?
Yeah.
It'd go forever. Yeah, that's the R. Okay. Okay. So it's only good for small voltages. Small voltage changes. It can be a big voltage all the way from ground, all the way over the whole operating range of this amplifier, but the voltage difference has to remain small enough to be linear.
So V1 and V2 have to remain closer one to the other.
Yeah, so you can't, it won't act linear for big steps in V1 or V2.
Okay.
V1 especially. Okay. Okay, so the dual circuit this is called RC low pass. Let me put this in a different color. RC low pass. The opposite is the dual of this is a CR, and that will be high pass. So let's imagine, how can you make a high pass filter out of this? High pass means it only passes high frequency and doesn't pass a steady state. Well, you can imagine how it is. I mean, you just swap the resistor and capacitor, right? If I do that, then I have V1. Instead of having a resistor there, you put a capacitor. Now I have a resistor here. And the output is where? Here, right? V2. And this will tie to some reference voltage like ground, just a fixed voltage. Okay, again, you have a C and an R. And now let's imagine what the response of this circuit is. By the way, I haven't drawn the time domain response. Perhaps I should do that for you to show what the time domain response looks like for the RC low pass filter. Let me do that here in brown. So let's imagine that I'll do this here. I'll try to draw it here. So imagine this is the time here. And now I put in a step input as a function of time. Make V1 in blue. And suppose V1 does something like this. And it's a small voltage step. Okay, what is V2 going to do? Let's draw V2 in green, I guess. Okay, so for this circuit on the left here, okay, what is V2 going to do? Well, for steady state, it'll do this. Right? But then because it's a low pass filter, if I step V1 suddenly, well, V2 won't change instantly because it has to charge up the capacitor, right? So it'll go up. And if you work out the mathematics, as I will in a minute, you'll see that it exponentially approaches the new value. And then when V1 steps back down, V2 will go back down exponentially. Okay, so that's a low pass filter. You see how it's kind of filtering the sharp edge here? Okay, let's do the same thing for the CR high pass. So I'll draw the same plot over here in the time domain. And again, an input signal in blue, V1. It could be the same step here. And now let's look at V2. Okay, now V2 doesn't have to have the same DC level. In fact, if this is 0 volts here, then V2 will just be centered around 0. In practice, inside a chip, it'll be centered around some voltage that's between VDD and ground. But for simplicity, I'll just make it 0 volts now. So now in steady state, the value of V2 will be what? If V1 doesn't change, V2 will just go to ground, right? There's no other voltage it can go to. So in steady state, it'll just be sitting here at ground. And now what happens when V1 suddenly steps up? It'll step up too, right? I mean, the capacitor will instantly couple this voltage change to V2. So it'll step up. If there's no other capacitor around, if there's no parasitic capacitor here, which you actually do have on the chip, if that is 0, then it'll step up exactly the same voltage. You can work it out. And now what happens? Now suddenly the voltage is high. You suddenly dump some charge Q onto here through this capacitor, and it's raised the voltage V2 up high. Now this charge Q leaks away through the resistor, but with the same exponential behavior exactly as for the RC low pass, right? It'll leak back to 0, some time constant tau. And then the same thing will happen over here, right? When you step down, it'll go down, go back up. And the same tau will happen here. And we'll work out later that this tau here, this time constant, is equal to RC in both cases. Resistance times capacitance. Now, how do you replace the resistor in the right half circuit with an transconductance amplifier? Just do exactly the same thing, right? I'm going to draw it down here in blue. So we have the same circuit, V1 here, input capacitor, and now we need some amplifier here that drives this point with the conductance, just like we had before. We're going to connect it up so that the output is connected to the minus input. Now this can be some reference voltage, Vref. There'll be some fixed reference voltage, and then the output is V2 here. And now the resistance, if this has a transconductance G, then the resistance will be 1 over G, 1 over the conductance. Okay, that's what you're going to test this week. You have on the chip a transconductance amplifier, just like you had before. On the chip, there's also a built-in capacitor with a value of 1 picofarad. So C on the chip is 1 picofarad, so E minus 12 farads. And you're going to set the current of this transconductance amplifier so that you get a particular conductance or equivalent resistance to give you a time constant tau, which is in the range that you need in order to sample it using the analog to digital converter. So you're going to compute the bias current on the amplifier such that you get a transconductance such that you end up with a time constant that's in a reasonable range. And then you're going to see whether if you actually set that bias current, you get the time constant and behavior that you expect. So that's the mission. Okay, so that's really all it's all about. Now, the rest of this is all just mathematics, working out, how you get these behavior quantitatively, and how you compute the frequency domain response. And I haven't shown you yet the equivalent frequency domain response for the high-pass filter. Right, so let's draw it over here. This blue here represents the frequency domain, the transfer function, the H, the frequency domain transfer function for the low-pass filter. What do you think it looks like for the high-pass filter, the CR high-pass? If I just drew it, say, in green. So let's say this is the RC, low-pass. And what do you think the CR high-pass looks like? What would you guess? And the circuits are, yeah, you can guess that it just looks like the opposite of that, right? So if I draw, say, I'm running out of colors here, but if I draw it, say, in red, I don't know, green for the CR high pass, and my color is not very consistent here. In fact, this whole thing is frozen up. I have to wait for the blackboard to catch up here. Okay, so I'll draw it in red here. So it turns out it looks just like this. So that's the CR high pass. It's the opposite. It doesn't pass low frequencies. In other words, the gain for low frequencies or DC is 0, right? Because here it's not copying the input voltage at all. It's just ignoring it. And then once you get to high frequencies, it'll pass everything. Is that all clear? Because these basic ideas should be, self-evident to you without all the fancy mathematics. And now we're just going to do the math and consider the large signal responses.
Just to be clear, 1 second. When V1 is high on the high pass filter, even though it's high, no voltage is being passed to V2, right? Because the capacitor is just like saying, no, I'm not passing that frequency, which is 0.
Yeah, the capacitor just blocks any DC current from flowing.
And how did we get a negative V2 there? That confuses me a bit.
Oh yeah, because when V2 is at ground, like it is here, can you see my mouse, by the way?
No, but if you draw it, we can see what you draw. Like,
Okay, you should actually, when I share the screen, you should see my mouse pointer, but I guess you don't. So when V2 is at ground, as I've shown in the red over here, then if suddenly V1 goes down by 1 volt, then V2 must go down by 1 volt also. Goes below ground. Now in a chip that can't happen because you're going to forward by some junctions, but in a linear circuit out of discrete components, for sure it'll go below ground here. It'll just go negative, right? So all of a sudden you're taking charge back off the capacitor.
okay.
Now it has to charge up towards ground again. Yeah.
That
Okay,
makes
thank
sense.
you. Okay, so I need to remind myself just a moment here while I find my own notes about what I was going to show you. Where did I put those though? Okay.
Also, Professor.
Yeah. Just call me Toby, by the way. You're welcome to call me Toby.
Okay. Then in the frequency domain, when we look at the log of V2 over V1, the change in the slope of the curve, like the red and the blue one, for blue for RC and red for CR, happens at the which frequency? 1 over tau?
Yeah, this frequency, that's, you're asking, what is this frequency here, right? What is this frequency?
Yes.
Where they cross over. Yeah, exactly. So tau is a time. So 1 over tau is a frequency, but it's not quite 1 over tau. It turns out it's 1 over 2 pi tau. This corner frequency right here, it turns out that this frequency, I should draw in a different color. It's not red or blue. It's green. Okay, well, choose green, right? A primary color. So this particular frequency here, F, which is called F3 dB. I'll tell you why that is later. F3 dB, it turns out that it's 1 over 2 pi tau. 2 pi, you divide the 1 over tau, which is a frequency in hertz, by 2 pi to go from radians. Yeah, actually, this 1 over tau is a frequency in radians per second. Radians per second. But to get hertz, you have to divide by 2 pi.
Perfect.
Okay, so the actual frequency is 1/6 of the radians per second. You'll see that's just the convention for radian, that a radian is 2 pi. There's 2 pi radians in one period.
Okay, thanks.
Okay. That sometimes fools people, right, when they're really trying to study, because the difference is substantial. It's a factor of 6. In other words, 2 pi is about 6.3 or something. So, you know, you don't want to make that mistake, especially in the wrong direction, right? Then you'll be off by a factor of 36 instead of 6. Okay. Okay, so now let's go here and make a new board here. So now let's compute the time domain response of this RC low pass filter. Let's just write the differential equations and compute let's compute this exponential decay of the natural response. So let's see RC low pass, what's called natural response. Natural response means the response to a disturbance. In other words, if you don't force the input to do something, you just let it relax, like you hit the swing and see how it responds after you give it an impulse. So we're going to do that by, to compute the natural response of this thing, we're going to rewrite this RC low pass filter as a resistor in parallel with the capacitor, both tied to ground. And now we're going to start out with the voltage V0 here at t equals 0. Okay, so you see it's the same thing, but now the input, which was V1, is just fixed to be 0. So we're not driving the input at all. We're just sticking some charge on the capacitor, which is equivalent to the voltage V0. And then we see how the charge leaks off the capacitor back onto ground. It's clear that it'll do that, right? Eventually the voltage V will end, this voltage V2 will end up at 0. because the charge that you put onto this capacitor will just leak off through the resistor to ground. That's clear, right? So let's write the differential equation of that. It's quite easy. We say that C, and this is R, we say that what's the current through this resistor, right? It's just V2 over R. That's the current through the resistor. That must be the same current coming off the capacitor. That's the capacitance times V2 dot. Right? C dV dt is the current. So those two currents have to be the same, right? So that's the full differential equation. And so now we can put it in a more familiar form, right? We'll multiply by R on both sides. And we'll say that R tau equals RC as the units of time, right? Because if I put the R, the way you can see it has units of time is that if I take R times C, I have to end up with a voltage when I multiply by dV dt, right? So it has to have units of time. Because if I multiply RC times V2 dot, I have to end up with V. So it has obviously the units of time. So then I can say tau V2 dot plus V2 equals 0. Okay, that's the differential equation. This is dV dt. dV2. Let's forget about this V2. It's just V. Okay, we'll just call this V. Okay. No, we don't need to write the 2. Okay, so we have to solve this differential equation for V as a function of time for t bigger than 0. Right? At t equals 0, it's some initial voltage, and we know it's going to go to 0. So we have to guess. One way is we can just guess what the function is. I mean, you might guess what it is. So I'll just guess what it is. I already know the answer. If you think about it for a minute, the only thing that makes sense is an exponential, because the only function where if you differentiate it back, you get back the function is exponential. Well, you take the derivative of any exponential, you get the exponential back again. And so we'll just guess that V of t is equal to e to the minus t over tau times V0. And it has to have e to the minus t over tau. That's an exponential decay because you have to end up with a dimensionless thing up there. And so if you do that, let's just check that that actually solves the equation, right? So now I take tau times V dot. Okay, if I differentiate this function with respect to time, I get back the exponential again times minus 1 over tau times V plus V equals 0. Is that true? Yeah. Minus V plus V equals 0. Yeah, so it works. So it's a correct solution. I hope that's not too tricky. It's just showing that there's an exponential decay for this first order low pass filter. That's all there is to it. Okay. It doesn't quite explain how it responds in the time domain to some arbitrary input. That's just the natural response of the input to a disturbance. Okay. What about the R? So what if you replace this resistor with a transconductance amplifier like this, and you give it a bias current IB, then what is the equivalent R, or equivalently, what's 1 over G, or what's the transconductance? You remember how that goes? So the I out here equals IB, that's the bias current, times, anybody remember what the function is? The tangent, hyperbolic tangent of kappa IB over 2 UT. Let's assume we're subthreshold here. So that's the actual output current. That's that this hyperbolic tangent function of B and I out. Okay, so now what we care about for the equivalent conductance is the slope of this thing. Now the derivative of tangent of x with respect to x just has a slope of 1. So that means that the G, the small signal equivalent GM, or transconductance, is just equal to, let's see, no, this is not correct. How come you guys don't? Did anybody see that? Kappa delta V. Okay. So that means that the transconductance is, if you differentiate this thing out, you get kappa IB over 2 UT. So that's the transconductance, which is 1 over the equivalent resistance. So you see how this has units of conductance? It's a current divided by voltage times some constant. Right? And again, it's subthreshold, so you just get back the thermal voltage. The only voltage that matters in subthreshold is this KT over Q, right? So it's really simple. So if you want a particular resistance, then you can compute what the bias current is that's needed to get that. Is that clear? Okay. I have to watch the chat here. Okay. There's a question from Keatsy. Why is the output conductance of the wide range transamp lower than the transamp? What do you mean lower? Oh, yeah, that's related to last week's circuit. I'll answer that later if you don't mind. But basically, the short answer is the output conductance is lower because the output transistors are longer, and so they have a higher early voltage. Like otherwise, there's no reason that the output conductance should be lower. It's because the amplifier is designed to have long output transistors to make higher voltage gain. Okay.
What's up, Professor Toby? The GM in this case has to be very, very low. I mean, we want it to be very, very low, as we wanted a large tau.
By the way, can you guys hear me okay if I put the speaker here, the microphone?
Yeah, it's perfectly.
Okay. Okay. So what's the question now?
Do we want a very large GM, so a very large tau? So we want a very low GM.
You want a small GM. If you want a long time constant, you want it to be weak, right? You want a small transconductance, high resistance.
Okay.
You want it to be slow, turn down the current. Makes sense, right? The lower you make, the smaller you make this bias current IB here, you know, the slower it's going to be, right? Makes sense. Less current coming out.
Yes, makes sense.
Okay. It all is very reasonable.
Yep. Thanks.
Okay. Okay, so now let's look at how to do the frequency domain analysis. This is kind of we can do the same thing. Let's do the analysis for the CR high pass here. Okay. The same equations, right? Just so you have it down. We want the natural response of the CR high pass. Well, we don't need to do that actually. I mean, it's the same natural response because it's exactly the same circuit for natural response, right? The CR high pass, I mean, you just put some voltage on the output of it and then the current leaks away. So it has the same exact natural response, just an exponential decay to the final value. We don't even need to do it. The differential equation is a little bit different because you're putting an input in at a different place. But you guys should work that out for yourself. You see, we'll do it a bit later too when we do the frequency domain response. Okay. Okay, now I want to show you something that I think is really quite interesting. It's the response to an impulse. So, and the relation of this to integrators and differentiators. All right. So let's do that on another picture here. So let's take a perfect integrator circuit. Sometimes this low pass filter is called an integrator and the high pass filter is called a differentiator. And I'd like to explain the reason why that's true in various different ways. Okay. So let me attempt to do it first with the aid of a delta function, Dirac delta function. So let's suppose that we have an input V1 and we have a perfect integrator circuit. Just integrates the signal V1 over time perfectly, right? It just integrates the signal value. Of course, it's going to explode in reality. But let's imagine you had a perfect integrator and it would just perfectly integrate the signal. And now as a function of time here, let's imagine our input is an impulse of infinite height and infinitely narrow width. So it's like a delta function. So suddenly you put in a million volts into V1, but only for a nanosecond. It's like you're suddenly putting a bunch of charge on the input. What's going to be the output of the circuit? Well, it'll be right. If it's a perfect integrator, it'll just integrate up that charge that you put there and make an output. So the response to this delta function input is like a perfect integrator. It'll just tell you that the charge changed. And what if the circuit, instead of being an integrator, is a differentiator? So it actually computes ddt of the input. Sorry, ddt. This is V1. This is V2. Okay, so now we can't put a delta function into it, because what's the derivative of a delta function? It's like the square of a delta function, right? It's hard to define it. But what we can do is put in a step. So if our input here, V1, is a step function, then we know the derivative of that is a delta function. It's like if it's a perfectly wide step, then the output, V2, is just going to be an impulse, right? The derivative is infinite, but only for an infinitely short amount of time. Is that clear? What I'm going to now argue is that this integrator is equivalent to an RC low-pass filter, but only in a certain frequency domain, and that this perfect differentiator is like a high-pass filter, but again, only in a certain frequency domain. Okay. In order to do that, I'm going to show you what happens to these circuits in the time domain, the real RC and CR circuits in the time domain. Okay, so let's do that. Okay, so let's imagine that we have the RC low-pass filter. And again, we have V1 and V2. And now let's choose, as a function of time here, let's put an input V1. What color did I use? I think blue for input, right? So V1 again is a step. It's a step function. We already know what the response is, right? The step. It'll be like that, right? And then if you wait long enough, it'll just go to some steady state. But what's the integral of a step? The integral of a step is exactly a linear function of time, right? Because all of a sudden, when you step up, as time passes, you add up more and more of the signal. So for short times, for short times or high frequencies, for short times, or equivalently, or equivalently high frequency, V2 is like the integral of V1. That's why it's called an integrator. You see how it integrates there? Because the response to a step is just a linear function of time. Okay, is that clear? Okay, so now let's look at the equivalent thing for the differentiator, or the CR high-pass filter. So V1 is here, V2 is here. Now we can't take a step function as an input. Instead, let's take a sinusoid. Right? And the reason I take a very slowly varying sinusoid, I want something that changes slowly with time. And so now my input is going to be a very slowly varying sinusoid. Just something like this. Okay. So the observation is that if V1 changes slowly with time, then V2 is going to be almost equal to 0. Is that clear? Because if V1 doesn't change at all with time, then V2 doesn't move at all, it just stays at 0. So if V1 changes slowly, then V2 is almost going to be 0. Right? So if I make V1 change slowly like that compared to the time constant tau, then V2 is just going to barely deviate from 0. It'll be like this. It'll just move a little bit. In that case, even when V2 changes a little bit, V2 will equal to I times R. And what will I be? I will be set by just how much V1 changes with time, right? So I will be C times V1 dot approximately, because V2 is almost equal to 0. In this case, you can see that V2 here is almost exactly equal to the derivative of V1, proportional to the derivative of V1. So that means for slow input or low frequency, V2 is approximately V1 is proportional to V1 dot. And that's why it's a differentiator. Is that clear? Okay, that's why they're called integrators and differentiators. Okay, so now let's look at the S plane, which is the sophisticated Heaviside method. So first I need to explain a little bit about this, why it's called S. So I need to explain a little bit about complex numbers. I assume most people know about this, but if you have a complex number, which is characterized by a real and imaginary part, we're just going to call that S. S is this complex number. It's equal to some real part, sigma, plus J times an imaginary part, omega. This sigma and this omega are constants, right? They're just a constant point in this complex plane where this is the sigma real axis, and this is the omega imaginary axis. So S is some point in this plane. Say it's say it's here. All right, let's say S is here, this point. So it has a negative real part and some imaginary part. Okay. So why do we do this? Because now we can take this magic function. This is what Heaviside realized. He realized that if you take a function of time, which is say that V equals e to the st, where s is a constant complex number and t is time, then this describes all kinds of decaying and exploding sinusoidal functions of time. Because these e to the st is equal to e to the sigma t. That's times the times the cosine omega t plus j. J is the imaginary square root of -1. J sine omega t. All right. So, it's a function that varies sinusoidally with time in this way, but it also decays or explodes with time according to the real part. So this general form for the voltage as a function of time is just, it describes all these, oscillating functions that decay or explode. Okay, is that clear? Okay, if you don't say anything, I'll assume it is clear. All right, so let's draw what this function e to the st looks like for different points in this complex plane of S. By the way, this is called the S plane. Okay, so let's draw it. Let's draw it for different points, right? So suppose we have a function here on this, right here on the imaginary axis. So suppose we have a point right here. Okay, so there's no real part. So sigma is equal to 0, right? So this is just a constant, but it's an oscillation. So this thing just represents a sinusoidal oscillation of fixed amplitude. Okay, what about a point out here with positive S, but no imaginary part? Now the omega is 0, right? So you don't have any sinusoidal variation, but this just represents a function of time. This is time, by the way. This just represents a function of time that just explodes. Okay, same way a point back here on the real axis, but with negative sigma represents a function of time where something just decays to zero. That's like your RC or CR filter, right? First order low pass filter. And how about a point out here or here? Doesn't matter which side, right? Because the imaginary part is not, it's just cancels. So that represents a function which is a decaying, say we take this point right here, that represents a function of time, which is say decaying sinusoid, right? So it gets smaller over time. So it's like the swing in the playground. You hit it and it oscillates for some cycles and then it goes to zero. And if I move further away on this axis here, that means it decays more quickly. So it'll ring for less cycles. If I go to a point over here, it'll decay more slowly. So the oscillation, the closer you are to this imaginary axis, the more cycles the oscillation will last. Okay. So e to the st is just a general complex function of time. In practice, you only measure the real part. It's a really nice way to describe such decaying or exploding exponentials. So now suppose you have some differential equations that describe some circuit and they're linear equations of functions of time. And then if you plug in, it turns out that if you can plug in e to the st and you just get a polynomial equation in S that solves the differential equations. And I'm going to demonstrate that in the example, for the example of the low pass filter. So let's do that for the first order low pass filter. Okay, so we're going to imagine that the solution for the first order low pass filter, I'll just draw the circuit again here. And we already had the solution, we already had the equation for that. We said that tau times V2 d, well, I'll write it out actually. Tau, I'll write the differential equation. Tau times V dV2 dt plus V2 is equal to V1. Okay, so now let's just imagine that let's imagine that that V is equal to e to the st, some function of e to the st. Okay, now when I differentiate this function with respect to time, if I take the derivative of e to the st with respect to t, I just get s times the function itself. So if I imagine that V, if V2 equals is proportional to e to the st, and plug that in, then I find the equation, which is tau times s plus 1 equals V1. Okay. No, this let's see. We have to put in a constant here. That's the problem. Right? V2 0. So tau s plus 1 V2 0 equals V1. Okay. This is still a function. Okay, so what we can see from that is that every time you get a derivative with respect to time and you're using this function e to the st, it just turns into a factor of s in front of the function itself. And so instead of having derivative function here, you end up with a polynomial function where tau is a constant, that's the time constant in your circuit, s is your complex frequency, and everything else cancels out in a way that I'll try to describe here. Sorry, this is V1, yeah, V1. Actually, this is V2. Okay. So now you can solve this equation for the transfer function h, which is V2 over V1, and it turns out to be 1 over tau s plus 1, h of s. That's the transfer function of this first order low pass filter in the complex transfer function. Okay, so remember S is your complex frequency. It's a point in this S-plane that represents generally just a point on the imaginary axis. That's the signal you're going to drive the circuit with. So if you take S equal to j omega, so that you're driving the circuit just with a pure sinusoid instead of some exponential, then you can compute the explicit form of this is equal to 1 over j omega tau plus 1. Is that clear? Okay, so what happens for low frequency here? If omega is small, if it's much less than 1 over tau, in other words, if omega tau is much less than 1, what does this h become? It becomes 1 divided by 1 plus a little number, so it almost equal to 1, right? So it's equal to 1 for when, let's see, let me write it down here. This approaches 1 when omega is much less than 1 over tau. So for low frequencies. What happens at high frequencies? At high frequencies, this thing dominates here, and it becomes 1 over j omega tau when omega is much bigger than 1 over tau. So here, even though it's a complex function, I mean, in this case, it's an imaginary number, but you can see that it goes down as you increase the frequency omega here, it goes down like 1 over omega, the magnitude of this response, this h function. Goes down like 1 over frequency. And so that's how you get that first order low pass filter response. Now, if you actually want to compute this, you have to take this complex function, which is 1 over j omega tau plus 1, and compute its magnitude, its actual magnitude. In other words, the length of this complex number. And in order to do that, you have to multiply the top and bottom by the complements, the imaginary complements of these things, and work out the arithmetic. And then you get the actual transfer function. That's done in the slides that I shared with you. I'm not going to bother to do it here. Okay? But that's how you do this S-plane analysis. I think this part that I did over here on the left here wasn't so clear. So let me do the same thing for the CR high pass. Okay, so let's do the same analysis for the high pass filter. So let's take the high pass filter again. This time I work out the equations. V1, V2, this is R, and this is C. So how can we work out the differential equations of this? So we know that the current flowing through here is equal to the current flowing in there. So we know that C let's see, this is the R here. Sorry, I did this the wrong way around. C, and that's R. Okay, so C, V2, so we know that V2 over R, that's the current flowing through the resistor, that's equal to the capacitance times V1 dot minus V2 dot. So it's the capacitance times the rate of change that the voltage is changing across the capacitor. Okay, so let's put the RC in there. So we know that V2 is equal to tau times V1 dot plus tau times V2 dot minus. And now we can write the equation putting the V2 all on one side. So we now have the tau times V2 dot plus V2 equals tau V1 dot. So that's a differential equation that describes how V2 responds to V1 changes. You see, it's only the V1 dot that's coming in. There's no steady state V1. So you know it can't respond to the steady state value of V1 because it's just not in the equation at all. Okay, so now let's plug in e to the st. So we'll use Heavyside's method here. We'll just plug in e to the st. And so then we get tau s plus 1 times V2 equals tau s. We put an s here because of the derivative, V1. So now we compute h. is equal to V2 over V1. That's equal to tau S over tau S plus 1. That's it. That's the transfer function. Is that clear? This is a little bit tricky, huh? Thinking about what S is. Remember, S is a complex frequency. Okay, so let's see what that looks like. Again, I'm going to plot the magnitude of H here as a function of j omega, the log of omega, all right? Okay, so I'm going to plug in that S is equal to j omega. In other words, it's a point on this imaginary axis. And what I find is for this high pass filter, if I work out the magnitude of this H here by multiplying by the complement of the number, then I find out that H looks like this for the CR high pass. And I'll draw it again here. Looks like this for the RC low pass. Again, this frequency this omega 0 is equal to 1 over tau. Yeah. Any questions? Okay. Okay, from this, we can work out a table also of how this RC and CR filters act like integrators and differentiators for what frequency domains. So let's draw this little table down here. Let me do that again here. Let's take the RC. Let's see, let's take CR. RC is in red, and CR will be in green. And in this table, I'm going to put the fact of whether it's a integrator or a differentiator or a follower as a function of frequency, right? As a function of omega W. Okay. Okay, so if you're much less than, if your frequency is much less than 1 over tau for low frequency, or if you're much bigger than 1 over tau for high frequency. So the RC filter, the RC low pass filter, does it act like an integrator or differentiator or follower for low frequency? This RC low pass filter.
Integrator.
Just a follower, right? It's exactly copies the input voltage. So the RC low pass for low frequencies acts like a follower. Okay, it's for high frequencies that it acts like an integrator. But the CR, let's see, that's the CR. It's just the opposite. For high frequencies, it acts like a follower. And for low frequencies, it acts like a differentiator. Right? When something's going up like this, that means it's like a derivative. It's like computing the derivative. When it's going down like this, it means it's acting like an integrator. And if it's flat like that, it's just copying the input signal. Okay. So that's about it. It's practically the last thing I want to show you, except for the large signal response. So let's talk about what happens in large signal now. And this is, by the way, this is a very classic examination question. We're very likely to ask you this kind of small signal, large signal stuff on an oral exam. So it's good to pay attention to this. So let's take this follower integrator. where we put a capacitor on the output. This is V1 and V2, except I'm going to draw them in color here, right? So V1, for the purpose of this slide, V1 is going to be in brown, and V2 will be in green. And now let's make a time domain response. And let's take an input signal V1, which looks like this. All right, so this is 0 and this is VDD up here. So that's ground, right? Okay. So let's imagine that we start with a small step up, then back down. And what will the output V2 do? All right, so we already said when the voltage difference across this transconductance amplifier is less than 100 millivolts or so, it'll act like a linear circuit, right? So we'll have an RC decay. Just like an RC filter. Okay, so but now suppose we make a really big step. So suppose this is only 100 millivolts. Okay, now let's make a 1 volt step. What's going to happen here? Is it clear? So again, if this is delta V on the input equals V1 minus V2, and this is I out on this axis. Here. Then what does that curve look like? Remember, it's a transconductance amplifier, so it has this hyperbolic tangent. So what happens when the voltage difference is bigger than a few UT? Then the current saturate. Yeah. What was that?
Yeah, I was going to say that you fill in the voltage with the current multiplied by the transconductance, and
Well,
until you have a different or divided by the transconductance.
I can't see who that is talking. So say that again.
You just fill in the difference in voltage until you have 100 millivolt, and then you go normal.
Right. So the current, that's correct. Yeah. So what will happen is the current at the output of the transconductance amplifier will just saturate at plus or minus IB. It'll just stay there until the voltage difference gets small enough. When the voltage difference gets small enough, it'll start decreasing. So what does that mean for the output voltage, V2? This is V2 here, and brown is V1. So what happens when you charge a capacitor C with a constant current? It just changes linearly with time, right? So instead of going exponentially, I mean, usually a linear system is characterized by the bigger the signal, the bigger the response. It has to be linear, right? That's what it means to be a linear system. In this case, the bigger the signal gets, it doesn't change the response. I mean, all it changes is that it has to go further before it becomes linear again. So now it'll go at a constant rate until the voltage gets small enough. And then when the voltage difference between V1 and V2 gets small enough, it starts going exponential again. And so what's the slope of this curve here as a function of time? It's a voltage, it's a time rate of change of voltage. What is dV dt there? You have a current, bias current IB and a capacitance C. So what's dV dt? Anybody know? Somebody must know the answer. I won't go on until somebody gives me the answer. What's dV dt there? The current is IB and the capacitance value is C. Just go back to the basic equation for a capacitor, right? CV equals Q. That's the capacitance, right? So CV dot equals Q dot equals I. So V dot is I over C, right? So the slope of this curve will be IB divided by C. Does that make sense? Okay, what about going down again? Now the current coming out of the capacitor will be minus IB. So again, it'll go down. It'll be slew rate limited. Now the curve will be minus IB. Obviously. So that's the large signal limit. Now you should work out for yourself with your sketch on your own piece of paper what's going to happen in a CR differentiator when you slew rate limit it. What do you think? So instead of responding exponentially, you put a big step in, and instead of responding exponentially to the step, recovering from the step exponentially, it'll just recover like a line, and eventually it'll go exponentially out. And so what does that mean? That means that there is no definition for large signal. There's no definition of a cutoff frequency. It's really a different kind of thing. It's defined by the slew rate limit. The slew rate limit is just the bias current divided by the capacitance that you're driving. That defines the maximum rate of change of the output voltage with respect to time for the natural response of the system. And you should easily observe that when you're measuring this stuff on the chip. Okay, that's it. That's all I wanted to tell you about it. You're probably going to have lots of questions during the experiments. I just want to show you the steps. I'm going to conclude with the steps for doing this kind of analysis. So what are the steps that you need to go through? Steps to get the transfer function h of s and the natural response. So what's the first thing you have to do? Right. Step one, you have to take your actual circuit and draw the small signal equivalent. The actual transistor circuits are very nonlinear, right? They're exponential and stuff. So draw a small signal equivalent circuit. And so you have something that looks linear with all the voltages and currents. Okay. What's the second step? You write your ordinary differential equations for that small signal circuit. Those are just functions where the output voltage derivative is a function of the voltages. It might be second order or third order or something like that. Then step three, replace all d dt by s. And if you have a second derivative with respect to time, you'll replace it by s squared. Because if you take every time you take a derivative of e to the st with respect to time, you get another factor of s in front.
Toby, so one question. So when we draw the small signal equivalent, we already take things into the S domain, right?
No. Small signal just means that all the transconductances are just linear. In other words, the change in the current is just linear with the change in the voltage. So when you go small signal, it means you always go around some DC operating point. So you imagine the circuit is already working at some operating point, at some steady state voltages and currents or voltages. And then you just say, what happens if you change the voltage a little bit? How much does the output current change? That's what small signal equivalent means. Is it clear? We'll do it for one more example after this for the source follower, which will make it more clear. Okay. Okay, so replace your DDTs by S, and then step 4, what's the next step? Okay, compute H equals V out over V in. That'll be a function of S. And in general, that will be some numerator function polynomial in S divided by some denominator polynomial in S. In our case, the numerator for the follower integrator was 1. The denominator was tau s plus 1. But for the differentiator, the numerator was tau s, the denominator was tau s plus 1. Had the same denominator in both cases. Okay. Step 5, and this is the only point that won't be obvious. Do you want the natural response in the time domain? If you want the natural response, then here's the trick. Find the S that makes of S equal to 0. In other words, find the solution to this equation d of s equal to 0. And then those particular s's, which are just constant frequencies, represent the natural response. Let me show you an example, or why that's true. This is the tricky part. So look at this equation here, this one. If I expand this out, and suppose I do that, if I write out this equation, then I can write that V out times D of S. D of S is a polynomial on S, right? That involves the R's, the C's, and stuff like that. Equals Vn times N of S. Okay, what does natural response mean? Natural response means how does V out respond when Vn is just equal to 0? In other words, I'm not driving the system with an input signal. So if Vn equal to 0, if this part here is equal to 0, then this whole thing over here is equal to 0, right? The only way that can be true is if d of s is equal to 0 for all V out. That's the only possibility, right? It must be that d of s is equal to 0 too, always. So then no matter what V out is, this equation will be true. So let's do that for the very simple case of the RC low-pass filter to show the natural response. And this, for the RC low-pass filter, I'll do it here in RC low-pass. Then d of s is equal to tau s plus 1. Let's set that equal to 0. What is the s that makes that true? S equals minus 1 over tau. Okay, so in other words, the natural response of the system is going to be e to the minus s is equal to the e to the s tau, right? It's e to the minus t over tau. So v of t. That's the natural response. You see how it comes out to be exactly the exponential decay in this case? It's really quite cool. So if you have a complicated transfer function, you know, where the s has like s squared plus something times s plus 1, then all you need to do is find the s's that make that denominator function 0. And those denominator s's that make the denominator 0 will represent the natural response of the system. In general, for a second order system like an oscillator, hopefully the real part is negative, so it's actually stable, it'll decay. But then it'll tell you how it's ringing, how many cycles it'll ring, what frequency it'll oscillate at, and all kinds of stuff. So it's a really handy method to find the natural responses. And it just reduces down to simple algebra and solving these usually quadratic equations. And we're going to do that later for second order filters. And after you do it for a while, you kind of get an intuition about this stuff. And it's extremely helpful in many, many domains, not just electrical circuits, all kinds of mechanical systems.
If we get a negative frequency, sorry, like for a natural frequency, for example, here, does that mean anything?
Is that?
If we get like a negative complex frequency for a natural frequency, like here, does that mean anything that's negative?
Anything where the, remember, this all has to be anything where the, I'm trying to open up this slide again. Anything where the real part of the S is negative, in other words, if it's on this half of the plane over here, of the S plane, where sigma is less than 0, then that represents a decaying response, right? Because e to the st will be e to the minus something times time. That represents decay.
Okay.
Is that clear? If it's positive, that's bad. Usually it means that your circuit will explode. It doesn't mean it'll go to infinity, right? Because it's always limited by the power supply rail. But if you have an oscillator, you want that. You want it to oscillate. But if you have a filter or something and you work it out and the S actually comes out to be positive, that means that it's unstable. It has positive feedback, sufficient positive feedback that it'll just explode and turn into an oscillator.
Okay, thanks.
But remember, you can still get oscillation even if the S is negative because of some large signal saturation. Like for example, suppose the feedback in your circuit saturates. That means there's not enough feedback. So then your circuit can still oscillate even if the S in small signal is negative. That's called a large, I don't remember what the name of it is, but it's a very common problem with circuits that you don't take account of the nonlinearities, the saturating nonlinearities, and your circuit ends up oscillating even when in principle it shouldn't in small signal. Okay, I hope this is all kind of helpful as a gentle introduction to using Heaviside's cool methods for understanding the transfer functions. In order to really understand this, you have to go through a little bit of pain yourself and work out the complex arithmetic. In other words, you should work out with your own hands what is the form of the magnitude of h of s. If I want the magnitude of this function, you have to work out, how to turn that complex number into a real number, which is the length of this vector. But you guys can work on that yourselves. All right. It turns out you'll get something that's like one. I'll just give you a hint what it looks like. The magnitude of this function will look like the magnitude will look like, let me draw it a different color here. It'll be like omega squared tau squared plus 1. So it looks something like that. And so that's a real number, right? But again, as you make omega really big here, it just goes down like 1 over omega, right? Because you're taking the square root of the square. Okay, good. If there are no other questions right now, I wish you good luck in your measurements. And I hope you appreciate that Chen-Chi has basically put his complete PhD work to the side for this entire semester to support you guys in this class. And so is Alex, a number of other people working on the class chip to try to bring up the things so you can do the measurements to the extent that at least that you can do them. And so please give him a word of thanks for that, because he's really put in a heroic effort. Okay, good. So I think next week, it's been really fun doing this stuff. I'm going to post the video of this lecture later, but next week, Giacomo is going to take over and he's going to start telling you about winner-take-all circuits, log domain circuits, and stuff like that. So I hope you enjoy that.